Okay, more theorems. I think yeah, more theorems. All right, we have 3 more theorems to go, and then hopefully there'll be time for an example.
These are in Theorems 2 slide or still Theorems 1?
Yep, these are in Theorems 2. So and the 3 theorems we'll be talking about are the shift, the derivative, and the convolution theorem. And the good news is we've actually already done the derivative. Although we haven't really, because it turns out to be an odd transform, we first introduced it in the odd basis sets, but it actually will go through the derivative as a formal theorem as well. Okay, shift, derivative, and convolution. The shift theorem. So it's f of t plus or minus t prime. Fourier transforms to phi of f times e to the I 2 pi, minus I 2 pi ft prime. Let's see the proof. Well, first of all, before we do the proof, should I illustrate what the heck that means? Okay. What's the best way to do this? Well, I'll use one of the examples in the lecture notes. So that way, if I butcher it horrendously, you'll have something else that you can refer to get it right. And that is if we have an impulse at 0. And we ask, what would it be if I moved that impulse over to t prime? What would its Fourier transform look like? In fact, well, yeah, we'll leave it in terms of time. It's arguably easier to, never mind. I'll go with this. Okay. What would you intuitively think? Might not be obvious intuitively in the time domain. It might be a little more obvious in the frequency domain, because this is 1/2 of an impulse, of an even or odd double impulse, right? And so it should Fourier transform as a cosine or a sine or some sort of sinusoidal function. And so if we take the Fourier transform of this, we should not be surprised if it ends up having that same sort of relationship, right? And so if I'm taking the Fourier transform, and in the Fourier domain, I have this e to the I 2 pi ft that ends up being a multiplier. What's that going to look like if I do the Fourier transform? I'm going to have the Fourier transform of the impulse is a constant, right? So I'm going to have a constant times e to the negative I 2 pi ft prime is phi of f, according to this theorem. Does that make sense to everybody? In other words, it's the Fourier transform of that, which is a constant, multiplied by e to the I 2 pi ft, corresponding to the fact that I've moved that over. Good? Sort of? Should I go through that a little more explicitly? Okay. We'll go through the example, give you a good picture in your mind's eye, and then we'll do the proof later on. So the example is, consider a shifted impulse. right? Yeah?
Why is T of 0 constant? Like the impulse at T of 0, why is that a constant?
Because the function is only of t. All I'm really doing is shifting my reference point in time or frequency. But it's not a variable. It's a constant, just like t0. The characteristic frequency, this is a characteristic time.
Basically saying you can change your T prime to whatever, add or subtract T prime, whatever you want.
So the question is, can you add or subtract t prime to make it whatever you want? You certainly can, but remember what we're trying to do is take functions and decompose them into basis sets that we can then manipulate. And so the actual function I'm trying to manipulate will dictate what t prime must be. Okay? So that is my function in time. I'm going to write this as this shifted. Not t0, t prime. Does that make sense? In other words, like if I redefine my variable to be t minus t prime, then I have a nice delta function at 0, and a nice impulse at 0. And then the Fourier transform of this, so this is delta at t minus t prime, right? That is my function is a delta function at t minus t prime in this picture. Yeah? So the Fourier transform of this, according to the theorem, should be whatever the Fourier transform of this is multiplied by e to the I 2 pi ft prime. So the Fourier transform of the impulse is a constant. So this, if the amplitude here is a, then the Fourier transform gives me a times e to the minus I 2 pi ft prime. T is not a variable. F is. That is an excellent question. What would that look like? Anyone remember Euler's relations? So I have phi. Oh, come on, don't do that to me. I have phi of f equals a e to the minus I 2 pi f t prime, right? So Euler's relations. Anyone remember what e to the x is? Oh, ix. Sorry. Otherwise, it's e to the x. You can write this in infinite series. What do you want to do? Never mind. E to the ix. Okay, everyone is obviously very, very up to date on Euler's relations. And yeah, that now that you see it, it's like, oh yeah, well that's what you meant. Exactly. Yeah, it's cosine x plus I sine x is e to the ix. So if I look at this function, what does it look like? It's going to look like a times cosine 2 pi f t prime minus I a sine 2 pi f t prime. So the real part of that function is going to be cosinusoidal with the characteristic frequency of 1 over t prime. Why is this not terribly surprising? Maybe it is, maybe it isn't. But what I had, that was what I had in the time domain that I Fourier transformed, right? If I was to add another one over here, what should I get? Yeah, that should be just the cosine part. It will be this. So it's not surprising in hindsight that when we do this shift and Fourier transform, we're going to get something that looks sinusoidal with a characteristic frequency consistent with that shift. Now it's going to have both real and imaginary components because it's neither an even nor an odd function. But the characteristic, this, if I see an e to the I 2 pi ft like that, I think oscillating function. The shift is t minus t prime. Actually, I guess this should be minus, right? Yeah, that's minus. I had that right. Okay. Now the proof. Everyone loves proofs, right? They're nice, because if you care about them, they're interesting. If you don't care about them, you can just think about other things and they don't matter. All right. I'm not at all cynical. No, I'm actually just, I mean, really, you're not going to, the proof, it's nice to know where they come from. It's really just sort of to satisfy my own, my own words as an instructor. There we go. I knew I could find the right words there eventually. All right. So the proof for the shift theorem. So that's the Fourier transform of f of t plus or minus t prime.
It's supposed to be a dt again.
Sure is. I don't know why I wrote ft. I'm going to write this in a sort of a curious way. I'm going to write this now as the integral from negative infinity to infinity of f t plus or minus t prime times e to the minus I 2 pi f t plus or minus t prime times e to the minus I 2 pi f. I think I want actually plus. So here I have added t prime. Let's say that the sign is positive. In this case, I've added a negative t prime. So here I'm going to add a positive t prime in the exponent. Would it help if I went back one more step? Or is there a question?
In the first equation, y on both sides were using f. I think one of them should be 3.
No, what we're asking is what is, this is what I should have the Fourier transform of big F is equal to. So it's the equality that was leading the, what?
Should the sign of the second t prime be flipped relative to the first one?
Yes.
Okay. So
Let me go
minus
back a
plus.
step. No, I have a plus here and a minus here.
Oh.
Should I go back a step to clarify where this came from? Because I'm seeing some confused faces. I'm going to write this instead another way. I'm going to keep this as that, and I'm going to multiply this by e to the negative I 2 pi f t prime minus t prime, which is 0, right? And e to the I 0, e to the 0 is 1. So I'm really just multiplying this function by 1. I can rewrite, if I have a sum of the exponents, I can write that as, in other words, e to the a plus b equals e to the a times e to the b, right? So I can break this term right here up into 2 exponents. So now I have 3 exponentials. And I'm going to take that first exponential and fold it into that middle exponential and fold it into the first. And that gives me then the equation that I had before of this equaling negative infinity to infinity of f t plus or minus t prime e to the minus I 2 pi f t minus or plus or minus t prime times e to the plus I 2 pi plus or minus t prime dt. So that and that net correspond to multiplication by 1. Okay. Here's the cool part. This is not a function of t. It's only a function of t prime. Yeah? Yeah, so I can pull it out. So I'm going to, oh, I need more space. Okay. So what does this look like? I have e, oh great, I'm back to red, sorry. E to the plus I 2 pi f plus or minus t prime times the integral negative infinity infinity of big F t plus or minus t prime e to the minus I 2 pi f t plus or minus t prime dt. Yeah? Okay. Close parentheses. It turns out that dt plus or minus t prime is simply equal to dt if I do the variable substitution. Do you agree or not? T prime is a constant. T is a function. So if I take the derivative of t plus or minus t prime with respect to t, I get dt again. So that means that I can substitute into this integral plus or minus t prime. And it's still valid. Is this integral, oh, come on, a function of t or t prime? The answer is neither. It is not a function of time because I'm integrating over time. So in other words, I could put negative infinity to infinity of f of smiley faces e to the minus I 2 pi f of smiley faces d smiley faces, and I would have exactly the same thing as I had there, right? That becomes a dummy variable. That t minus t prime doesn't actually matter because I'm integrating over it anyway. And this would still be the Fourier transform because you still have the frequency dependence in this integral. And so this then becomes equals e to the I 2 pi f plus or minus t prime times phi of f. And somewhere I'm off by a sign, if I am not mistaken. No, no. Looks good. Or this could be just as easily written plus or minus 2 pi f t prime times e times phi of f. And this, again, equals the Fourier transform of t plus or minus t prime. So that's the proof for the Shift theorem. Okay.
What's in front of the I?
That did not. Plus or minus. I just moved that plus or minus out to the left instead of leaving it where it initially was. And this should be nothing there either. So that's just e to the I plus or minus 2 pi ft times phi of f. Satisfying? Yeah. Okay, so that takes care of the sine. Let's see, we've done the derivative. That's the next one. Proof for the derivative. Wait a minute, we have introduced the shift theorem. I mentioned the derivative and the, yeah, we're on Theorems II. I mentioned I haven't gone through all three of those theorems though. I got stuck on the shift theorem. Okay, so let's move on and cover the next two. So I want to get through all of the theorems before the end of class, and I don't want to run long, and we have 15 more minutes. Okay? So we'll hold off on the proofs. I went through the proof for the shift theorem in detail. I think I'm going to hold off on the derivative and the convolution. Okay? And if there's time at the start of class on Tuesday, maybe I'll cover those. But I want to make sure to get through both of those before heading out. So the next theorem in this section on theorems part 2 is the derivative. And we've already covered that one. Basically, is that if you have if f of t is a Fourier transform pair partner with phi of f, then d dt of f of t equals I 2 pi f phi of f. Which is pretty funky. The one I really want to spend, any questions on this one before I move on? It doesn't make sense right now potentially how that could be used or how it's actually really useful because anytime you have a factor of frequency that you want to remove, you can Fourier transform the derivative. Okay. Maybe you're not as awestruck as you should be on that point. Examples.
Should that be equals or double for the second line?
Oh, yes, you're right. Thank you. That should be Fourier transform.
The reverse operation is just a sign flip.
Yeah, the reverse operation is only different in the sign. So d df phi of f Fourier transforms as negative I 2 pi t f of t. Okay, last one is the arguably most important one, and that's the convolution theorem. Convolution happens all the time in electronics. What is convolution? Let's talk about what that is first, and then see why there's a theorem. See how the theorem benefits that manipulation. There we go. So convolution. We'll define the convolution. The result of convolution as being c of t is defined to be the integral of f of t times f t minus t prime negative infinity to infinity. I think it makes a heck of a lot of sense, before I even talk about any theorems, to give you a couple of examples of what convolution looks like and does. So let's take, and we represent convolution, wouldn't this be 1 or 2? These don't have to be the same functions. Let's do an example. We're going to take a rectangle. Actually, we're going to make it a nice big rectangle. and convolve it, and that circled cross is what is the symbol we will use universally as convolution. Convolve it with a Gaussian. So what does convolution look like? Well, in fact, I'm just going to make this blue. And it might be that function, for example. So what does convolution look like? What it convolved, we get this t minus t prime. So what we do is we take the blue one, and we flip it, and then we slide it across. And at every position, we're integrating. Right? Because this is a function of t prime. This is one t prime value, another t prime value. We're marching through t prime, and every t prime value, we evaluate this integral as a function of t. And that gives us a function just of t prime. What is it going to look like? Well, if I take this, I wish there was a way to do this graphically, but I'm not that. I think there's a way to. Okay, maybe I can. Maybe I'll try. How about that? Keep. Let's see if this works. Oops, wrong one. Okay, so as I slide this function across, the integral is 0 because they don't overlap, right? And then as it starts to overlap, the integral increases, right? And then it increases, and then it keeps on increasing until it stops, it saturates, it plateaus, right? And then it stays plateaued. And then it starts sliding off the back end and decreases again. That worked out way better than I anticipated it would, by the way. So what is the net result going to be? The net result, qualitatively, I need to go to this before I can do that. Is something that looks like that rectangle, but smoothed over the integral of the Gaussian on the edges. And it's a little bit broader. Why is this important? Because if I have an electronic signal and I measure it with something, electronics, that have a finite bandwidth, the net result that I measure will be a convolution of the electronics and the raw signal. So convolution shows up all the time. Yeah. Okay. So that's convolution. The convolution theorem is really cool. So now you have a mathematical explanation of what convolution is, but really the most important thing is you have this picture in your mind's eye of flipping, sliding across, and integrating. And it's that integral over this thing that's sliding across that gives you the convolution. So convolution theorem says that if big F, sorry, F1 of t has a Fourier transform partner of phi1 of f, and F2 of t has another Fourier transform partner if I have a function that I can write as the convolution of two other functions. We're thinking basis sets, right? So I'm going to decompose something. If I can write it as a convolution of two functions in the time domain, then in the frequency domain, there's simple products. So it turns out that's good and that's bad. It's good in the sense that we've taken something that's a really complicated convolution integral that we have to solve numerically every point along the way, and turned it into something in the Fourier domain that's a simple product and can be very easily deterministically written down. That's the good news. That's the cup is half full way of looking at this. The cup is half empty way of looking at this is that if I have a basis set function that involves a product, then in the Fourier domain, it's going to involve a convolution. And so you want to avoid, if you're decomposing things into basis set functions, you want to avoid products in general and write them in convolutions anytime you can, because then they Fourier transform much more intuitively and easily in the Fourier domain. So should I give you a quick example? Okay, so let's look at a Gaussian. I'll tell you this function. So it's two Gaussians offset from 0, symmetrically offset from 0. We'll say that this has, how much time do I have? Yeah, probably just enough time. This has, we'll call it a t prime, and this has a t naught. And this is a negative t naught, but has the same t prime. What is the Fourier transform of this? It will ultimately turn out to be that. How did you arrive at that? And so what he said was this, that the Fourier transform of this was going to be the product of a Gaussian with a cosine.
Well, you have two Gaussians,
Mm-hmm.
so it's a convolution over an impulse, which is going to be Gaussian, and it's an impulse on both sides, and it's cosine.
Yes. I'm going to re-say what he said in my own way, but it's exactly right. How do we make this function here on the left? Well, it's not trivially obvious, but let's try one thing. Let's take a Gaussian centered at 0 with a characteristic with t prime and convolve that with an even double delta centered with a characteristic time constant at t0. So if I flip the cosine, the even double delta, it's exactly the same. As I slide it across, the impulse, shall I do the same trick I did before? Let's try it. I did the same mistake last time too. That's so funny. So we're going to make this thing and then slide it. There we go. Slide it across. As we slide, okay. As we slide the integral 0, I'm going to get an integral that's non-zero, and then the origin of this is right in the middle here, right? And then it goes to 0 again when t equals 0, right? Or t prime equals 0. And then it's going to slide. I really shouldn't use t prime as two different things. I'm seeing that now. Delta t. Okay, I can make this. I know what to do. That's delta t and t naught. Okay. As we slide this double delta across, remember the integral over the delta function is 1 if it's normalized. So it's going to duplicate the value of that Gaussian function every time it intersects it. And so it's a replicating function. If you integrate, if you convolve with an impulse, it just gives you back exactly the same thing. The only issue is that our impulse is offset. Offset positively and negatively plus or minus t0. And so it duplicates the Gaussian, but duplicates it about the offset points. And so I can write now the Fourier transform exactly in this way. That is the Fourier transform. This is the time domain response I can write as the convolution of the Gaussian function and the even double impulse. So I've got Gaussian delta t convolved with even double impulse t0, and delta t is small, t0 is large. And so if I Fourier transform this, I'm going to get a large Gaussian multiplied by a small cosine, qualitatively. We can put in all the appropriate numbers if we have real numbers in there. But I know that my delta t is much smaller than my t naught, and so therefore my delta f is going to be much greater than my f naught. And so what's this going to look like? It's going to look like a cosine that starts and stops with a Gaussian envelope. Pretty exciting, huh? Okay, lots of information today, lots of tools that we've developed. The next thing we'll be doing, so prepare yourself, go through these, get some familiarity in advance. The next thing we'll be doing is exercising these muscles and building up problems using Fourier transform basis sets. So that's what you can expect on Tuesday. All right, that's it. You can hand in the paper copy to me. Starting a little pile right there.